We're going to start on the next module today, which is algorithms and algorithm analysis, which is a little bit more theoretical than we've been doing up to this point. So there's going to be an introduction to some a little bit more math than usual. But we've already given motivating demonstrations of this throughout our development of the list-based data structures. And just to remind you about that, I've got yet another demonstration queued up here that we can take a look at. Remember the index-based retrieval operation on a list, right? With an array-based list, you can immediately jump to the ith element, right? You can't do that with a linked list. If you want to get to the ith element on a linked list, what do you have to do? You have to start at the beginning and then iterate and do I traversals to get to that point, right? And just to show you what that looks like again, what I've got here is a program that will generate n random numbers, and I'm just initially doing 100 here, and it'll sum them all up, right? So very, very simple program here. All I'm doing is taking a timestamp at the beginning, taking a timestamp at the end, after I've summed all of those numbers up, and then I'm reporting the results, right? Initially, what we've got here is a linked list. So how bad is this? Right? Well, if I run this with 100, it's immediate, right? Extremely fast. In fact, it was done in a matter of 0.0006 seconds. If you want to parse out that time there, okay? But remember that we are online, so if you have any questions, go ahead and post to Piazza or to the YouTube live stream. Just make sure. I forgot to make sure that. Yep. Okay. Everything's working. All right. So let's go ahead and increase this by a couple of order of magnitudes here to actually start observing its runtime. So I'm going to go ahead and kick this up to I don't know, 10,000. Right. Okay. And let's see how much time this takes now. Okay. So 0.06 seconds now. Right. So we went up by a factor of 100, and it seems like it's now slower by some factor of 100 or something like that. Let's go ahead and kick it up to, say, 100,000. And now we're going to start seeing some real time measures here, right? Summing 100,000 numbers here. There, it took about almost 6 seconds here, right? That was an order of magnitude about how much bigger is that? Was 100 times as big or something like that? Oh, what was the other one? 0.06 seconds or something? Yeah. This is 100 times slower, even though we only went up by a factor of 10. Right? So we're going to go up to a factor of 10 more, up to 1 million. Right? So if our past observations are any indication of our future observations here, then this will be 100 times slower. 100 times 5 seconds is 500 seconds. 500 seconds is about it's 10 minutes or so, under 10 minutes. Right? Let's go ahead and just go ahead and start executing this. Right? What if and by the way, is 100 or 1 million elements that much? Nope, that's not big data at all. Right? 10 million elements. 100 million elements. None of that stuff is big data, right? But we're seeing here the consequences of our decision to use a linked list. Now, don't take this as gospel truth that linked lists are bad implementations of lists. They have a trade-off, right? They have other operations that are actually more efficient than an array-based list. But while we let this experiment run in the background here, I'll go ahead and fast forward and show you what the results are going to be. Right? Now, what you have here is time in seconds on the y-axis, and the list size as thousands of elements. So the 200 on the bottom, that's 200,000 elements. Then 400,000 elements, 600,000 elements, and I incremented this by, I think, 50,000 elements or something like that. At the very end there, you've got 1 million elements, which is what we're actually running right now. And it's going to be about 500 seconds, which is what we estimated it, right? And the blue tick marks here are the actual empirical results of me running this experiment over and over and over again, taking an average and stuff like that. The red right here is what's called a quadratic regression. And I knew that this was going to be quadratic up front because of some theoretical analysis that I'll show you in a second. But also look at that curve, right? Does that look like a nice linear function to you? Nope, it's going up, right? A nice linear function would look like this, right? Just a straight edge here, right? With some sort of a slope, right? All right, so looks like our estimate here is going to pan out, but that's just because we thought, oh well, I saw it go up by a factor of 10, and then I observed that it was 100 times slower. Why, right? Let me go ahead and stop this because I don't want to wait here for 10 minutes. Right? We've got pizza to eat upstairs, remember, right? And let me just go ahead and really quickly show you the consequence of changing your data structure. I'm not going to change any of this code here, okay? What I'm going to do is I'm going to change this to an array list instead. And now I'm using Java's linked list and Java's array-based list. Let me go ahead and run this. Did it take any observable time at all? Nope. 0.17 seconds instead of the estimated, 10 minutes over here or so. Okay? So these things matter. What if I were to go up to 10 million? 100 times slower is going to be on the order of a couple of hours with the previous implementation. What if I went up to 100 million? 2 hours turns into 120 or 200 hours, which is now weeks, right? Not a little less than right? Yeah, it's going to be more than 10 days or almost 10 days, right? If I go up to a billion elements, now what are you thinking? Years, probably, right? So, first of all, let's figure out why this is, okay? Now, think about this as being a linked list, okay? On the each iteration, you are doing some sort of work, right? The work that we're doing for a linked list is starting at the beginning and going to the ith element. So our work here is going to be a node traversal. Okay? Now, on the first iteration, when I is 0, do we have to traverse any nodes to get to the first element? No. Right? So 0 node traversals. On the second iteration, where we want the second element, the element at index 1 now, how many iterations do we have to do? Well, you start here at the head, and then you just have to go one more over, so 1 node traversal. On the second iteration, or the third iteration, I should say, you have to do 2 node traversals, ... right? So you can kind of see the easy pattern here. To get the ith element, what do you have to do? Start at the node and do I traversals to get to that node, okay? On the last iteration, which would of course be n-1, how many node traversals do I have to do to get all the way to the end of the list starting from the head? n-1. So this is all the work that I'm doing. Right? Now I am doing some other work here. For example, I'm getting the element out of the node and then I'm adding it to some grand total, right? But this is what I want to focus on here, right? There might be some other work that I have to take into account, but let's go ahead and figure out how much work is actually being done here by taking one big giant sum. How many total number of node traversals am I doing using this code? Right? So let's do some math. Right? The total number of node traversals is, well, 0. I'm not even going to include that here. 1 plus 2 plus 3 plus 4 plus ... plus I. Remember, that's at the ith iteration. And then we go all the way up to the last iteration with it, which is n-1. Okay? You can write this in a nice summation form where I is running from 1 up to n-1, right? Because that's the variable that we're using, I, of I. Right? 1 plus 2 plus 3 plus 4. Now, does anybody know a closed form solution for this? If not, that's okay. Let's go ahead and label this as Gauss's formula. Because Gauss is the one that came up with it, or is credited with it at least. Oops. Oh. Okay. Low battery mode. It's 100%. Anyway. I, if you run it from 1 up to n of, of I is going to be equal to, does anybody know it? Yeah. N times n plus 1 all over 2. It's the classic example of using induction to prove this. Right? If you're taking 235, you've done induction and a proof by induction. You might have actually used this as an example or something, right? So we don't have n over here. Instead, we have n minus 1. When I take n minus 1 and plug that in for n, and then also plug it in for the other n, what do I have? N minus 1 times n minus n plus 1 and minus minus 1 ends up being n all over 2. Let's expand that out. Right? We'll go ahead and go with 1/2 n squared. Then what? Minus 1/2 n, and then minus 1/2. Right? Do all of those terms matter? Well, they do. I mean, if you actually want to apply Gauss's formula, right? I did it right? I think I did. Oh, yeah, 1/2. Where did that come from? Now that I'm thinking about that, there you go. There we go. That's good. Is that right? All right, good. Told you we're going to do some math here. All right, so which one of those terms is far more important than the other one as far as the amount of work you're doing? N squared, right? So let's go ahead and ignore this term. Right? Now 1/2 sitting out front, is that all that important? No, not when you consider the growth rate of that function. When we get down to what really matters here, this is an n squared function, right? Which is why I thought, oh, well, it's probably n squared, right? So maybe we want a quadratic regression to fit this curve right here, right? And so I performed a quadratic regression, right? This is a quadratic function, right? It looks something like if you've got the traditional, come on, there we go. If you've got a traditional xy axis here, what does your quadratic function look like? It's a parabola concave up, right? We're going to ignore this end, and we'll talk about why we ignore that end eventually. But it's this nice curve that goes up like this, okay? Get rid of that. It's kind of ugly. All right. So we have some theoretical basis for thinking that the behavior of this code that we just wrote is going to have some sort of quadratic behavior. And then I ran this experiment and got some empirical data that matches that. So those two things kind of reconcile with each other. Okay. Now let's put that into perspective. Okay. Why? Right? Why is this happening? Right? Oops, sorry. There we go. Both from a theoretical and empirical perspective, the code seems to have a quadratic behavior with respect to the amount of time it takes to execute. Okay? So what I want to do is I want to start developing a framework for not having to run these experiments. Instead, I just want to develop a framework for repeating that kind of theoretical analysis that we just did, and then coming up with, well, this seems like it's linear, or it seems like it's quadratic, or something like that. Right? Before we do that, how bad? Let's put this into perspective. Perspective of how bad is our linked list code. Right? So here is the actual quadratic regression that I ran. It came up with this formula right here. That's what I used to derive this red line right here, this nice smooth line. Okay. The coefficient out front here for the n squared term is not 1/2. In fact, it is 0.00064101, right? Because that's scientific notation right there. The coefficient over here is not is not 1/2 either. It's some small value, 0.01. And there's not a 0 like we did with our, over here, you called me out on my bad math, and there was no 0 on this this part right here, right here, right? But over here with the quadratic regression, there is. That's kind of capturing, in fact, it's 9.78 seconds, right? That's kind of capturing the fact that you have to set up the experiment, that you have to run the Java virtual machine or run something, right? There's some cost that's not actually related to your actual algorithm, right? So why is this coefficient not 1/2? Well, because it's on a computer, right? It's measuring how long a computer actually takes to do these operations, right? One operation of, say, traversing from one node to the next node, then that can be done in a fraction of a second. Those fractions of seconds, though, add up because you're doing n squared of them every single time, right? And plus some linear cost over here, right? And so that's what eventually we get this equation here that we can go ahead and follow this quadratic regression over here. By the way, it is almost a perfect fit, right? The correlation coefficient here, a perfect fit would be 1. This is 0.994, right? Obviously, there were some sampling errors here that it wasn't perfectly fitting this curve, but it is damn close, right? So close. Right? Now, I only went out to 1 million because I only had the patience to sit there and wait for it. I didn't even wait for it. I just ran it in the background and then came back later on. But let's go ahead and map it out and see what would, from a theoretical point of view, using this red line here, what if I went out to, instead of 1 million, what if I did go out to 10 million? Right? So what would that be? 10 million elements. Now, the way that I would do that is I would take 10 million and plug it in for n right here, plug it in for n right here. That's the number of seconds. I would convert the number of seconds to hours, days, et cetera, et cetera. Give me your estimate. I think it was, 10 minutes before? So this ends up being hours, right? In fact, with that equation, actually, I didn't run the original experiment on this computer. This computer's faster than whatever I ran it on before. But if you use this equation, it comes out to about 17.5 hours. So let's go up to 100 million. What do you think now? And again, it's quadratic, right? Let's think about quadratic first. So if I went from, say, n to 10n, right, and it took me time t before, and the behavior is n squared, what will it take me now? Remember that it's going to be n squared. That's going to be equal to, what happens when you square 10? 100 n squared, right? So it took you n squared before, now it takes you 100 times slower. Right? So with that in mind, what's 100 times slower than almost a day? Many, many days, 74 days. Right? What if I went up to 1 billion? Many, many years, decades now, 20 years. Right? So, does that sound like a good algorithm? No. Again, the real solution is to use an array-based list here. Or, better yet, you can use a linked list, but you don't start at the beginning every single time you want to go to the ith node. Remember the painter. What do you do to the painter that was walking back and forth every single time? You yell at him to pick up the paintbrush and take it with him. Right? You can do this with a linked list. You just need to make sure that you are using a better for loop here instead of getting the ith element every single time. Right? In fact, I did a linear regression, but I didn't show it here. Why do you think I didn't show it here? It wouldn't show up. Where would it be? It would be almost coincident with the x-axis right here. Right? It would be down here, all the way. You wouldn't be able to see it. There is such a stark difference between 10 minutes, nearly 10 minutes, and 0.7 seconds, you're down here, right? So I didn't bother putting that in there at all, okay? In fact, I'll just tell you, what if we did a linear behavior? Right? Let me go ahead and back that. There we go. All right. 100 million elements would be less than 1 second instead of 18 hours. 100 million elements would be 10 seconds instead of 74 days. 1 billion elements, that's still going to be a lot of work, but you're talking about minutes instead of decades. Okay. So the takeaway with this motivating example is these things matter, right? There is kind of, especially with certain companies, a kind of an overemphasis on big O analysis, which is what we're going to do ultimately, and too much focus on theoretical analysis and stuff like that. Not enough focus on actual technical skills. But I do want you to have the takeaway of this from this motivating demonstration that these things actually do matter. Right? They do matter in practice. This is not a toy example. This is an example that I've adapted. I've seen this out in the wild in several different instances. And I knew right away, nope, that's wrong. Let's change it, make a pull request here, right? Don't do that. Don't have a blind index-based get method on a generic list right here. What happens when I've got a very large linked list? This ends up taking 20 years to compute. Right? Now, in those code bases that I've taken this from, they probably never bothered to do a load test. Right? They never had any lists more than 100 elements or so, and so they never really cared. Right? But these things do matter. Right? Okay. All right. So it should be clear at this point that computers, right, or actual engineering computers here, and more generally, more mathematically, algorithms require some sort of computational resource. For example, the one that we just measured was actual time, right? Like physical time. Or another way that you can measure it is CPU time. I've done a couple of demonstrations before of it, maybe in Computer Science 1 or so, but you can actually parallelize things, right? What you can do is you can take a task and then break it up into 10 tasks and then run all of those tasks in parallel using multi-core processing, multi-threaded processing, right? But still, you have if you have a task that took 1 hour and then you put it out to 10 different processors, and each one only took 6 minutes now, right? Because you're dividing it by 10, right? You're still doing a computation time of 1 hour. It's just that you're spreading it out so that you can do it in parallel. That's what we mean by CPU time versus physical time. What is another resource that algorithms might require? Time is money, so you could always say money, right? You could buy CPU time on Amazon Web Services, right? And there is a cost associated with that. So you could always bring everything down to money. But what's another resource that a computer requires? Memory. That's the other obvious one, right? And if you run out of memory, you can always download more, right? What other? Oh, that's a joke. Right? It's not my joke either. Right? Isn't there a website? Download more RAM. There we go. Yeah. Download RAM. More RAM, legit, 100% legit. Sure. Yep. What other? So think about your phones. Time, memory, that's not that big of a concern because you're not going to be doing a bunch of scientific computing on your phones. You're not even going to be doing some AAA gaming on your phones, right? So it doesn't matter if they're that fast. It doesn't matter if you've got a lot of memory. What is the bottleneck with respect to your phones? Not even really processing power because, again, you're not going to be doing any, high-level stuff on your phone, right? What? Battery, right? Power consumption, right? How many people in here would take, like you need to upgrade your phone, and you've got a choice between a phone that is twice as fast, big deal, versus a phone that takes half as much power and therefore twice as much battery life. Which one are you going to go for? Probably the battery life, right? Because that's more important for that particular device. Right? What about other resources? Sending things through the air, right? Network bandwidth or throughput. The amount of data that you can shove through a network, that's called its throughput, right? How much can you get through at one time? And that's typically actually the biggest bottleneck to processing. Even your phones are faster than they can process data faster than they can receive it, right? The network is still by far the slowest bottleneck in computing. In fact, it is still better, or I guess you could transport more data by simply just putting it on a bunch of hard drives and shipping those hard drives somewhere else, right? A truckload of hard drives will get to a destination before you can send it across the fastest network connection, right? And that is still the case. Right? What about maybe some of you are taking, say, 230 or 231, where you are designing circuits. What is a measure of a resource in a circuit? So simpler is better, right? If you can create a circuit with fewer number of wires or gates, right? So the number of wires, gates, right? Then that means that all of your resources go down, right? The power consumption goes down. The area on the die that you have to print your circuit on goes down. Because fewer gates, fewer wires means smaller circuits, and you can fit more of them onto a silicone die, right? One that people don't generally think about is idleness, right? Or utilization. There is no reason to purchase an entire Amazon Amazon computing center if you're just going to serve one website out of it, right, with 100 users, right? And so if you do make a huge investment in hardware that's idle most of its time, right, then you've basically wasted your upfront investment in the actual hardware. It would be much better if you had higher utilization and only one machine, and that's what virtualization is all about. You can have one physical machine with 20 virtual machines on it, right, that don't have a high load, don't have a high usage or utilization, but altogether they are fully utilizing that hardware, right? Are all of these things important? Yeah, right. These are all important engineering concerns and considerations. Right? But if we are looking for a universal abstract framework from which to analyze algorithms, do these things matter? Probably not, right? Think about history. Do you think so the first computer was introduced, the first actual working computer was introduced in the 30s or 40s or something like that, right? Do you think that was when algorithms were born? Nope. Algorithms are way, way older than that, right? One of the very earliest ones would be Euclid's GCD algorithm, right? Dating back to the, 4th century or something like that. But of course, we had multiplication and addition even before that, right? Before you even had writing, you had to add, I've got 2 cows, and then I added another cow, so I've got 3 cows now, right? That's an algorithm, adding multiple things together. How did you do that, right? Well, you had a process. An algorithm is nothing more than a well-defined process for computing something. Algorithms are far older than that. Algorithms are thousands of years old. Right? Just because we have computers now that are fast, computers are only decades old, right? Just because we have computers now that are fast doesn't mean that those algorithms are any faster. What it means is these coefficients in the analysis go down, right? If you take your hardware, like the hardware that I ran this experiment on, and I take the same experiment and I move it over to hardware. This is an i9, so you can't get much better than that, can you? All right, whatever. I get M2 is better. I don't know. It's just less power consumption, I think, right? So there you go, an engineering concern. For a laptop, power consumption is more important than getting a faster processor. Anyway, if I were to take this over to the HCC and put it on a much faster computer, right? Then those coefficients would go down, right? If it's twice as fast, then those coefficients would be halved, divided by half, right? If I went back in time to old computers, those coefficients would go up. But what would not change? This n squared right here, right? If I went back 1,000 years before, where we were doing all our computations on a piece of paper, right? Then there would still be the same number of steps to compute a GCD, a greatest common divisor, 1,000 years ago as there are today. It's just that those steps can be done, each individual step can be done a lot faster, right? So algorithms are invariant, right? The behavior and efficiency of algorithms is invariant over time and the type of hardware you use, right? Hardware, software, et cetera, right? From a theoretical perspective, we want an abstract notion of what a resource is. So we're not going to concern ourselves with engineering details like the number of wires or the network or how fast a particular operation is on this computer versus how fast it is on that computer versus how fast Euclid can do it on a piece of papyrus, right? We don't want to look at it from that point of view. We want to analyze algorithms from an abstract, general perspective. Because an algorithm is invariant. The same algorithm that Euclid developed 2,000 years ago is the same algorithm that we use today. It takes the same number of steps. It's just that those individual steps are a lot faster, right? What matters is the performance of the algorithm with respect to the input size, right? Not any particular machine, language, architecture, etc. Those are all valid engineering concerns, which is why if you have a resource-intensive task that has to, like a scientific computing task, and you want you're doing, I don't know, some large matrix computation or something, or, for example, the one that I was talking about yesterday in a completely different class was computations that were performed on the first real automated computer, the Harvard Mark I, right, in World War II. They used it to do some computations to find out if it was feasible to collapse a bunch of uranium and have it explode. Sounds familiar, right? World War II. They were working on the Manhattan Project and they didn't know it. They used this Harvard Mark I computer to do all those computations. If you have, now fast forward to today, if you have a scientific process that you have to have efficient and you have a choice between languages, what language do you use? Performance is important now. Now it's an engineering concern. What do you do? Same thing that everybody does. Write it in C, right? Python, because we know Python. Well, guess what? The math library in Python is nothing more than a thin wrapper to the C math library, right? MATLAB or even Java. If you look under the hood of Java, guess what it does? It makes calls to the system C library, right? Because why? C is way faster and more performant than any of those languages, right? Python is going to be orders of magnitude slower. Java is going to be orders of magnitude slower, right? Now, when you're serving, say, I don't know, the latest YouTube hit or stupid video or something, then performance maybe doesn't matter. Then different engineering questions come in, right? Network bandwidth, that's way more important than what language you wrote it in, right? But from a more general abstract perspective, we don't want to have to worry about any of those details. When you actually have to go and engineer something and build something, yes, those all become important. But when you're just analyzing algorithms independent of those resources, right, then you don't want to have to worry about those details. What orders is the rate of growth. Right? Oh, good, it worked. Right? Algorithms predate modern computers by thousands of years. Right? Algorithms do not suddenly become efficient just because you upgraded your hardware. The individual operations become faster and more efficient, but overall the number of operations remains the same. So what we want to calculate is the order of growth, the rate of growth as you increase the input sizes. Larger inputs leads to slower performance, means you need more resources, more time, more memory, more power, more whatever, right? That is all part of a general trend. And that's where we want to look at these things, okay? I don't want to get into too much math just yet, but let's look at a couple of examples, right? All right. And also motivate how we're going to look at these things. Now, I just drew the... Oh, sorry. There we go. I'm glad that I looked back often here. Now, I just drew the x-axis and the y-axis, okay? The x-axis is going to be the input size. And I'm not going to label it as x because that would imply it's the Euclidean plane. I'm going to label it as n. Why? Because n tells you what kind of a number is n in your head, just intuitively. An integer, right? Why don't we consider real numbers? Is there such thing as, say, a list of size 10.5, 10 and a half elements? Does that make any sense? No. Does it make sense to have a list that has -5 elements in it? No. So, for that reason, we are going to restrict ourselves to integers, and we're not going to consider negatively sized inputs. Right? I'm only going to look at the first quadrant of the Euclidean plane here, and as things go up. Okay. What about the y-axis? For our purposes, it can be time, but what I'm going to label this as is number of steps. Right? Eventually, we're going to call this number of elementary operations. Elementary operations. Now, we are going to map monotone increasing functions, right? Here, I'll show you a monotone decreasing function, a function that looks like this. Does that make sense in the context of algorithms? What is that doing? As you get larger and larger on your input sizes, the computation time goes down? Does that sound like any computer you've ever heard of? Nope. So, we're only going to consider monotone increasing functions. For example, a linear function. What's the general form of a linear function? an plus b, right? So the a out front is some coefficient that's capturing how much time or how many resources does each individual operation take, right? If you're adding up numbers, how much time does an addition and then load that back into a register in the computer take? And then you're doing n of those additions. B is capturing how much overhead there is to actually, start the program, to get the ball rolling, to load it into memory or something like that. Okay. What's another type of function? What? Quadratic, right? That looks, something like here. I think I can get it to make it look nice. Yep, I can. Cool. All right. What's the general form of a quadratic equation? an squared plus bn plus c. All right. And again, those coefficients are capturing the idea that individual operations have some sort of a cost. Okay. What's another one? So think back to, well, this is linear, right? And we call linear search because it has linear behavior. That's actually going to be our first example here. But give me another search algorithm. Binary search. Do you remember binary search's behavior? Logarithmic. Looks something like this. Ooh, nice. It did it. All right, and I'll just label this as log right now. Right. Okay. How do we measure the growth rate of functions? You may or may not have Calc 1 under your belt already. That's all right. For those that do have Calc 1 under their belt, right, how do we measure the growth rate of functions? Do you remember? No? So if I take a function, say n squared, and I take the, what is that thing? The first derivative. What do I get? 2n. In other words, this is the growth rate. The growth rate itself is linear. Okay. What if I took and I'm simplifying these things here, so I'm getting rid of all their coefficients because I don't care about it. What if I took the first derivative of a linear function? What's its growth rate then? 1. In other words, constant. Right. This is linear. What's the growth rate of a log function? By the way, what log is this? Not all logs are the same, right? That's a different log. That's the natural log. Why do we call that the natural log? Because it's base e, which is 2.71 ... Why is that 2.71? In whose book is that natural? In a mathematician's book, that's natural. Why does a mathematician think of e as being natural? What happens when I take the first derivative of e to the x? It's e to the x. That doesn't happen for any other base, right? So we are not mathematicians. I mean, some of us are, but this is not a math class. So we are computer scientists, computer engineers, right? Self-respecting computer scientists. What is our base? 2. Why 2? Binary, right? Base 10 is for all the other humans, non-mathematicians, non-computer scientists, right? Our base is base 2. So when I write just log, know that it's implicitly base 2. It doesn't matter. Why? We can all live in harmony with the, well, we can live with natural log, but we can also speak to each other and translate each other by using the change of base formula. Right? All logs are the same in the end, right? This is the same thing as some constant out front, log base a of n. Right? So we can all live happily here. But when we want to compute the growth rate of a log, now we need to change the base. What's the growth rate of what's the first derivative of log base 2 of n? Does anybody know? You change the base, so it's natural log of 2. That's just some constant, who cares? And then what? Divide by n, right? Again, ignore that constant out front and tell me about the growth rate of a log function. Is this constant right here? Nope. Is it growing like a linear function? Nope. In fact, it's going down. Right? The growth rate is going down. The function is still monotone increasing, but the growth rate is getting smaller and smaller and smaller and smaller. For all intents and purposes, a log in practice is no worse than a constant. What would a constant look like here? There you go. That's perfect. It doesn't get any better than that. Right? It doesn't matter what your input size you have here. Your algorithm will take the same amount of resources for an input size of 5 as it will take for 5 billion. These other functions, though, they grow. Right? Larger and larger inputs means more and more resources. Right? And we want to quantify that. I want to come up with a framework for saying, oh, that algorithm is linear, or that algorithm is quadratic, or that algorithm is linear, or logarithmic, right? Because then we can say, based on our understanding of growth rates, a linear function is better than a quadratic function. This is a bad algorithm. It's going to take you 20 years to compute 1 billion elements. This is a good algorithm. It'll only take you 2 minutes to compute 1 billion elements. This is an even better algorithm. It'll take you a matter of, hundredths of a second to compute, right? And this is even better, right? It's going to stay the same no matter what. Right? That is the framework that we want to develop here. To do that first, though, we need to be able to define what is an algorithm. So, you tell me, what is an algorithm? An algorithm is an unambiguous sequence of instructions for solving a problem. That's what you would get if you pulled out Webster's, the dictionary, right? And that's going to be sufficient for our needs. That is not a mathematical definition. A mathematical definition would be a Turing machine or lambda calculus or something like that, right? Some mathematical model for what computation is. That goes beyond this course. If you're interested in that, you might be able to see it in 310, Computer Science 3, right? What exactly a Turing machine is. We're not going to go that far. We're going to stick with Webster's for now, okay? An algorithm is not a Java program. It's not a method. It's not a function. It's not a snippet of code, right? So how do we describe an algorithm just given this dictionary definition? Right? That is not Java code. That's not C code. That's not Python. We use something called, and here I'm going to relabel this section, pseudocode. What is pseudo? Latin, Greek, I don't know. What is it? It's fake, right? Pseudoscience. What else puts pseudo in front of it? I don't know. Say what? Pseudonym? Yes, fake name, right? Pseudo, and then name, right? Then that's a fake name. A pseudonym is an alias or something like that. Excellent. So, what is pseudocode? Well, if it's fake code, there ain't no rules. If there were rules to your pseudocode, guess what you would have? A programming language, right? There are rules to writing Java. There are rules to writing C. There are rules to writing Python. If you put in too many rules, guess what? You've got yourself a programming language. So instead, we have just general guidelines. What is good pseudocode? Good pseudocode makes use of plain English, right? Makes use of good mathematical notation. Right? It doesn't use any language-specific constructs. Right? It provides necessary details without too many unnecessary details. Right? Okay. Let's just go ahead and get into it with a couple of examples here. Now, again, if I attempted to give you hard and fast rules for your pseudocode, then I'm telling you to build your own programming language, right? And I don't want to do that. Instead, I'm just going to give you general guidelines. In fact, what I'm about to do is I'm about to follow LaTeX, my typesetting system. It has a package called Algorithm 2E, and I use that for typesetting pseudocode. But again, it's a programming language. LaTeX is a programming language, so there are rules to writing pseudocode. But these are just general guidelines. You can change the styling in LaTeX. Okay. Good pseudocode labels the input and labels the output with any expectations that it has on those two things. Right. So what we're going to do is we're going to develop pseudocode here for, say, for linear search. Remember what linear search is? The problem itself, right? So given a collection of elements In fact, I'll call that collection A. And there are elements A1, A2, dot, 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 AN. Right? And a key, K, determine. Does there exist? Do we have this notation yet? Backward Z. Does there exist? I'll leave it out then. Does there exist an element A in A such that A is equal to the key K? Okay. Or if you want a more mathy notation, does there exist an A in the collection A such that A is equal to K? There we go. There's the math 235 way of doing that. Okay. So, my input. What is my input? Is it an array? Is it a linked list? Is it a Python dictionary? No. What is it? A collection. Is it a collection of integers? Is it a collection of doubles, strings, students, etc., etc.? Collection of things or elements. My pseudocode is going to be general and generic, abstract, right? Just like when we parameterize a piece of code, right? We make that into an abstract piece of code that polymorphically can be applied to many different types. I'm going to do the same thing with my pseudocode. A collection of elements, and I'll give it a label. A1, A2, dot, 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 AN. Ooh, nice label. What did I do? Implicitly, I told you how many elements are in that collection. N, right? Did I start at 0? Nope. That's a computer scientist thinking. We're now going to have to think like mathematicians. Do mathematicians start their indexing at 0? Nope. And a key, K. Is that key an integer, a string, a double? I don't know, right? My output will be unelement A in A such that A is equal to K. Right. What if I don't find any such element? That's perfectly possible. That's called an unsuccessful search. What should we output in that case? Note here, I'm also saying output. Do I say I return it? Or I system.out.println it? No, I'm just saying output it. Whatever that means for your particular language. Right? What do we do in the event of an unsuccessful search? Do we throw an exception? Do we return null? Do we return a negative index variable as a flag value to indicate that it was an unsuccessful search? Nope. I'm going to just go ahead and return phi if no such element. Greek, right? Phi. It's a placeholder for nothing. Okay. All right, help me out with the pseudocode here. What would be the step-by-step process, not using any particular programming language here? Maybe for each A in A, right? I will be a little bit Python-y here, right? If anybody knows any Python, that you have this colon, right? And that's how you start a loop block, right? If A is equal to K, stop and output A. Did I put did I put curly brackets? No, I did. I was kind of Python-y. There's a great video that I just saw that is kind of a joke on Python of, hey, you don't have any of those those nasty curly brackets. Instead, you just have white space errors. And then he holds up this ruler. Where is the error on his screen? Trying to determine where's the white space error because it's not properly indented, right? Anyway, what I'm going to do is I'm going to use something that is completely out of the norm for any language whatsoever. In fact, well, you can get this in IDEs. In fact, let's look at IDEs generally have this. All you have to do is collapse this, right? But that's not something that you type. That's just a feature of your IDE. You can collapse this block, expand that block, etc. Right? You've got this vertical line. It's kind of faint. You can't see it very well on the screen. But you've got this vertical line that tells you where the block begins and where it ends. Right? And that's what I'm going to do here. In fact, this is what I do in LaTeX. Do any languages have a for each keyword? Not many. One does that I know of. PHP. You can use for each as one keyword. Did I specify what equality meant here? Was I calling dot equals or strcmp in C? And if that was equal to 0, then they were equal and output true, right? Nope. Whatever equality means, keep it general. It's just a collection of elements. Did I have semicolons anywhere? Nope. In fact, now I'm rethinking, I don't even want that colon right there. Forget about that. Right? All right, once I get done, then I output phi for an unsuccessful search. There's some good pseudocode, right? Good mathematical notation, right? Mathematical notation for a set of elements here. Phi as a placeholder. I don't use equals equals here, did I? Nope. I'm using these vertical lines here to denote code blocks. Good pseudocode. All right, how do we analyze that pseudocode? It's going to be a 5-step process. 1, identify the input. Already done. 2, identify the input size. Already done, because we wrote good pseudocode. The first 2 steps are taken care of for us. Step 3, identify the elementary operation. 4, analyze it with respect to the elementary operation. 5, provide an asymptotic characterization of it. But we'll have to do that next week because we want some pizza. All right? All right, so we'll continue there on Tuesday.